So yeah, the thing that Stuart didn't mention is that I've not always been at Roehampton. I started there like 7 and a bit years ago, but before that, 4 different schools, 18 years, including 3 years as a primary head teacher, which sent me prematurely grey at the time, although time is rapidly catching up with me now. So much of that time as an ICT coordinator, teaching lots of things across the primary curriculum. I want to start by taking you back, in some ways, to an earlier age, where we got very, very excited about all of these lovely ICT tools and the way we could embed them across the whole breadth of the primary curriculum. There are some illustrated on the screen behind me. Tim talked about many, many more this morning, and that was so inspiring, of how we can use technology to extend, enhance, enrich children's learning across all subjects, not just this little bit of the curriculum which we used to label ICT, which we now label computing. Back in 2009, before they let me loose on the curriculum, Sir Jim Rose, bless him, came up with this model of ICT at the core of the curriculum, alongside literacy and numeracy, that ICT would cease to be a subject in its own right, but everything that a child would need to learn about the use of technology is something that would be embedded across the curriculum. So all of that spreadsheet stuff, don't teach that in an ICT lesson, teach that during a maths lesson or a geography lesson. All of the stuff about making PowerPoint presentations, put that into English lessons, put that into history lessons, so that we moved away from the subject as having a body of knowledge. And at the time, I got really quite excited by that sort of vision for ICT as a glue, which could hold the curriculum together, which would provide opportunities for children's creativity to flourish and give them, tools to do really interesting things. We then sort of rejig the whole thing and say, let's not do that. Change of government, as you're probably only too aware, and new government comes in and says, no, we're going to ditch Jim Rose's proposals for that. We're going to do a new thing. Lots more rigour, lots more sort of academic, serious subjects, and replacing the old ICT curriculum with a new subject called computing that Stuart's already spoken about. We start the new computing curriculum with this phrase, this ambitious vision for what we're trying to do here. A high-quality computing education equips pupils to use computational thinking and creativity. That's really the objective of this, is to think about problems from this sort of computational perspective, but also to be creative. Does anybody know the second bit of this sentence, though? There's a reason given for this. The reason why we want to do that is so that they'll come to understand and, be empowered to change the world. It's not just a thing in and of itself, computational thinking and digital creativity, important as they are, but this is about your pupils coming to some understanding of how the world works, and yes, being empowered through their creative work to make a difference, positive difference, to that world. And isn't that what you should be doing as a school anyhow? Teaching children to understand the world and teaching children to make a positive difference to that world. We talk about this a lot. We get very excited about this. Our friends at Ofsted, if they're going to come in and inspect computing, very, very easy thing to do. You just go up to the child and ask them 2 questions. Have you understood the world? Have you changed the world? And if they answer yes to both, then job done, really. Okay. But it goes further than this. The next sentence, which we don't talk about so much, I think is really important and enshrines this vision for computing isn't actually just a thing in its own right. Computing has deep links with mathematics, with science, with design and technology, and provides insights into both natural and artificial systems. And that actually enshrines what we're trying to understand here about the world. It is maths, it is science, it is D&T, it's other things as well, as I hope we'll get to before this presentation's over. Our friends at Ofsted, let's hear it for Ofsted. Okay, a muted woof over there, just finished your inspection, that's very good. Okay, that's great. So when Ofsted were allowed to say what they would look for in a computing lesson, David Brown, who was mentioned earlier, came up with this slide. And the really interesting one for me here is his third bullet point. The curriculum is broad and balanced with all 3 computing strands, the computer science, the information technology, the digital literacy, all covered well for all pupils in computing lessons and or across the school curriculum. 4th bullet on his side, links with other subjects in the school are productive in strengthening pupils' learning in computing. That this was part of Ofsted's then quietly published criteria for what good, or indeed outstanding, computing would look like. I've had to, by the way, cover up the Ofsted logo on the slide, but everything else I can use under the terms of the Open Government Licence. So, anybody been involved with barefoot computing, using any of the barefoot? How are they going down? Yeah, right. That's really okay, that's good. Did you get the trainer in? Did you get somebody to come and do a barefoot workshop? Sign up on the website. They'll come at BTS looking after barefoot now, and they'll come in and do free training for you around these lovely barefoot computing resources. The idea for barefoot is about, you guys know how to use technology, and you guys know how to teach well, but many of you, or many of your colleagues, don't really have much background in academic computer science, strange as that may seem for primary school educators. So barefoot is about filling in just enough of that computer science subject knowledge to be able to teach the primary computing curriculum well. And what we've done with barefoot was to say, let's take all of the computer science ideas and link them to the other topics on the curriculum. So Bill Mitchell at BCS Academy, his favourite example is, how do you plan the Viking invasion? A topic in the history curriculum, of course, that's all about coming up with a sequence of things, breaking a big problem down into smaller parts. So we take the computer science ideas and link them to other bits of the curriculum. For Barefoot, we kind of got to the nub of what we mean by this computational thinking thing. We say that there are a number of concepts, things like logical reasoning, things like algorithms, sequences of steps, sets of rules, things like decomposition, breaking big problems down into smaller parts, things like generalization of patterns, things like abstraction, about removing or putting to one side unnecessary complexity, and making judgments, stepping back and evaluating things. I hope you're thinking to yourself, I don't just do those during computing lessons. Those are things, those concepts of computational thinking apply across the whole of the curriculum. You want children in English lessons, in history lessons, in science lessons, reasoning logically, spotting the flaw in an argument. You want children in maths lessons thinking about the steps they go through to solve a problem, particularly when it's a really big problem. You want children in science thinking about the method for their experiment. You want children over in design and technology thinking about the recipe for making pizza or whatever. That these concepts, yes, I'd argue they're best learnt through the context of computer programming, but they're concepts that can be applied in a whole range of other contexts. And similarly, the approaches that Barefoot advocates of tinkering, playing, look what you were doing up on the carpet earlier today, of making things, of fixing things when they go wrong. Did any of you have Lego models that didn't work? Did you have to do that debug? I'm glad to hear it, okay? You need to tick that box for the assessment exercise here, of keeping going when things get hard. And yes, of working collaboratively, as you all evidently were earlier. Those approaches, they're not just things you want in your computing lessons. Of course they're not. But they're things which seem particularly effective when it comes to teaching computing. Who here is working in nursery reception, early years foundation stage? Good. So glad that you are here, because you guys are doing this perfectly. Characteristics of effective learning summarize all of this computational thinking stuff. If you're not sure how to teach computational thinking, go and spend a morning over in reception, in nursery, and see how they get children thinking what we would call computationally about problems. Inside Development Matters for Characteristics of Effective Learning, what do you want children to do? Think of ideas, find ways to solve problems, find new ways to do things, make links and notice patterns, make predictions, test out their ideas, develop their ideas of grouping sequences, cause and effect, logical reasoning again, plan, make decisions, solve a problem, check how well things are going, evaluation for us, change strategy as and when needed, and reviewing how well the approach worked. All of that is on my previous slide about computational thinking. Everything you need to know about computational thinking you learn in kindergarten. We build on that foundation later. I've presented alongside directors of engineering for whole nations at Google and said, is this what you want for your engineers? Yeah, that's pretty much the job description for a Google engineer. Okay, they don't take them straight out of nursery, but I think they probably could, because that's exactly what they're looking for. And shouldn't we just carry on with that a little bit further into the school? I hope you do. I really do hope that you do. So what happens in nursery? What happens in reception? Children choose their own problems. My guess is that the children in this photograph were not set the task of transport these crates from this position to the other position. They chose a problem that they would have a go at solving. And yeah, that's a big problem. You've got to decompose that. You've got to work collaboratively as a team. Children in nursery and reception look for what objects have in common and what objects are and the differences between objects. Later on, if they study computer science to a sufficiently high level, they'll be taught about classes and objects and properties and methods and things. But the foundation of this is laid through sorting little bits of polystyrene into two groups, or putting teddy bears into order of size. There's a thing about how many things a child can sort into order of size. Apparently, up to a certain age, the limit is 3, but try it with your own pupils. Again, they work collaboratively to solve big problems. I worry a little about this picture, by the way. I know it's very blurry, but do you notice already the gender roles here? The boys are doing the manual work, the girls are taking a managerial or supervisory role. It starts very, very early. It really does. Okay. And in nursery and reception, practitioners give children things like this to play with, or possibly the brightly coloured plastic ones with the bobbly bits on top. Stuart, other construction toys are available. These are Froebel blocks. 19th century German kindergarten, invented by Friedrich Froebel. He had the idea of give children wooden blocks to build things with at a very early age. And you'll see that in your nursery or in your reception if you have one attached to your school. Why do teachers still do that? Why are teachers still giving very, very young children building blocks to play with? This is not a merely rhetorical question. Okay.
Because they work.
Because they work? Because the children work or the building blocks work? Okay, right. Work in what sense? What's the objective here?
Do whatever they want with them.
Oh, yes! This is about their choice. This is about some sense of autonomy. Empowering children from an early age to be able to make their own choice. Why stop later? Really? Okay, so they work. Any other reasons? Yes, let's not deny that. Being able to move these blocks is really important when it comes to later on being able to pick up a pencil or stroke an iPad screen or whatever format we're going to do writing it. So yeah, fine motor skills. Anything else?
Teamwork.
Teamwork. Typically it's a group of children working together. Other things? Somebody said imagination. Absolutely spot on. Generally, children are working creatively with these. What you do not see in reception and nursery classrooms is the teacher makes one on their desk and says to the children in the class, go and make one just like mine, please, or gives them the build instructions to work through. So yes, creativity, imagination. Anything else?
Problem solving.
Who chooses the problem?
As they construct,
Yeah.
they will encounter problems.
They will encounter problems. You'll see very young children trying to build the tallest thing they can, and sometimes encountering difficulties with that. So yeah, other things? They're all doing very, very well, except in a really patronising way. Okay. Yeah, yes, absolutely. There's a physicality to this. I think Froebel, and after him folks like Piaget, would have said it's through playing with things like this that a young child comes to understand some of the properties of the world in which they find themselves living. That the number of blocks doesn't change. The shape of each block doesn't change. Yes, its orientation does, but the shape of the block is a stable thing over time. The space it takes up doesn't change. It can be transformed. It's still the same volume. And yet, if you pick a block up and let go, what happens? I have a room of 40 primary educators and nobody knows. This is worrying. Thank you very much, Stuart. Okay, I think that's still on the national curriculum. Yeah, you should be. Okay, but you don't teach that. You weren't taught that yourself. Well, the fact that none of you knew is worrying. Okay, but I was assuming actually, yeah, I guessed that, but that was a trick question. Okay, you learned that gravity works downwards through playing with building blocks like this. Not through being sat on the carpet and said, children, gravity works downwards. Which way does gravity work? It's through an experience of playing with toys like this. Nobody in the room has said yet, and I hope nobody is thinking, no. In our nursery, in our reception, we give them these to play with so that they become construction workers when they grow up, or so that they become architects when they grow up. Yeah? Generally, we feel primary education, particularly nursery reception, too early for vocational training for the construction industries. Okay? Some of your pupils will. Famously, Frank Lloyd Wright, great American architect, went to a Froebel kindergarten and played with these things, and in his memoir wrote how that early experience had influenced his later development as an architect. Okay, the next slide is missing. So yeah, Frank Lloyd Wright buildings look a lot like this. Similarly, your pupils, yes, when they're learning to program, they're learning about how the world around them works, and they're learning to express themselves creatively to solve problems. Yeah, so a certain element of functional skills involved with that as well. But it's not so that they all go and get jobs in the software industry or become academic computer scientists. Heaven forbid. We don't teach poetry in primary school, so we have more professional poets. Perhaps we need more professional poets. But the reason for including it on the primary curriculum is about expression of creativity and our understanding of the world. Ditto computer science, ditto programming. We do this computational thinking in lots of other ways as well. So putting on a play. Anybody already started rehearsing for the nativity play or Christmas play? Okay, it's too early. It really is too early at the moment, okay? But this is a big problem. How do you solve this? You break it down into smaller parts. How do you organise the play? You have a sequence of things that happen. Maybe a script that you follow on a good day, some of the time. How do you organise all of the costumes and so on? Well, you manage the complexity. You, I hope, are not making the costumes. You've got other people to do that, and you're relying on them doing that well. So we have so much of this computational thinking through something like this, or indeed something like this. So no lecture or workshop is complete without some reference to the importance of phonics. Okay? I've mentioned phonics, I can move on now. But algorithm understood as sequence set of rules. Isn't that what you're teaching? When you teach a child how the OR phoneme is converted into graphemes, you're giving them a set of rules that they follow. And there are a number of different contexts in which each particular rule will apply. And so you have there some way into algorithm as set of rules as well as sequence of steps. And of course, this is something which the machines can do now. Here's the moment of truth, folks. So we step out of the deck and have a go at this. Okay. I'm speaking in a normal voice at a normal pace without having trained this beforehand. I wonder how accurate it is at transcribing exactly what I say, ? Okay, I've got to turn it off, otherwise it just keeps on doing that. Yeah? That somehow Google, bless them, have got some way of understanding those phonemes that I was just spouting out there and translating them according to the rules into normal voice without having trained this beforehand. I wonder how accurate he is transcribing. Okay, there was a few mistakes in there, that's probably my fault. But broadly speaking, it's got the phoneme grapheme correspondence rules, and the other direction works as well. So we have here Scratch X. Who's using Scratch already? Scratch is so cool! Anybody using Scratch X yet? These are like the untried, untested, secret extensions to Scratch, one of which does text-to-speech conversion. So we have Talking Gobbo here. Here we go. So click me, and we type in something for him to say. Anybody remember any Govian non-words from the phonics check? Sorry? Flummer. Oh, very good. F-L-U-M-M-E-R? Okay, whatever, it's a Govian non-word. We could try Govian, actually, because that's a non-word as well. Can I pass the phonics check? Okay, and let's see how it gets on with that.
Flummer, Govian. Can I pass the phonics cheek?
Okay, it was close enough, wasn't it? You'd have given it the mark for that, I hope. So, again, that phoneme-grapheme correspondence, or in this case, grapheme-phoneme correspondence, is encoded there. It's not looking up how to say flummer in a big dictionary somewhere. It's decoding the particular graphemes. And teaching children, or getting children to think about phonics that way, I think that's worth doing. I really do. Links with computing. Okay, and then, of course, okay, we will pause for a moment. 2 minutes. Could you please write down your recipe for pizza? Hold on to that thought. Did you write down, because we're going to read some of these out, folks, a recipe, your recipe for making pizza?
Do we tweet you these, Miles?
No, I'm just going to take them verbally. I want to tweet recipe for pizza in 140 characters.
No, that's fine.
Okay. Pizza. Please tell me you're not Googling how to make pizza. Salt, flour. Sounds beautiful. Strawberry pizza. Small ingredients. Okay, I've got crumbs in my head. Right, let's pull this together, folks. Who here has a really detailed, step-by-step recipe for pizza? Thank you very much, sir.
You really want me to go into it, do you?
Well, we've only got.
Well, if you're taking the dough,
Okay, let's start.
500 grams of flour, 320 grams, because you weigh your water, you don't measure it.
Density of water.
50 grams of olive oil, 20 grams of fresh yeast. Okay, so you roll that out, then you can put. Once you've rolled it out, then you can put your pesto and puree sauce down. If you're that way inclined, 2 kinds of cheese might be buffalo mozzarella and cheddar. And then you top it with some nice fresh basil leaves, olives and anchovy.
I love the anchovy. Pine kernels, capers. How far do you want to go with this? Really nice recipe, thank you very much. Did anybody include more detail than that? Okay, so Stuart,
It's like different detail.
go on then.
Get phone.
Yeah.
You said
Go on.
790-442. Get phone. Open Domino's app.
Yeah.
Go to meal deals. Choose pizzas. Sit back and relax.
Absolutely fine, yeah. I mean, really, no problem. Let me just deal with the first slightly more detailed
I object to the second one.
That's fine. We have multiple methods for solving the same problem here. That's great, it really is. There isn't one unique recipe for pizza. But even in your wonderfully detailed recipe, there was layers of abstraction that you didn't go anywhere near.
Yes.
Okay, so you told me you would take 500 grams of flour, which is great. You've not gone to the trouble of planting the wheat, of grinding the corn, of making the flour. That sort of thing you're assuming somebody else has done, which is fine.
I
I would.
need to grind flour.
Yes, and similarly, no time have I ever done this with a group of people, and anybody's told me that firstly you plant the tomatoes, wait for tomatoes to grow, harvest the tomatoes. We always assume a certain level of detail. And generally, folks will include something like knead the dough in their recipe. When you're doing this with very young children, you cannot say to them, knead the dough, because that's a procedure that needs defining. You need to unpack what we mean by knead the dough. You need to teach that new word to the particular computational system, in this case children, that are doing the particular task here. In Stuart's case, which seems a very, very high level of abstraction, well, that's fine, but it's not quite as simple as Stuart makes us think. Firstly, he had to choose a supplier for this product, and he's gone with Domino's. And of course, the correct answer was Pizza Express, but don't worry about that, it's fine. It's not. Then there's an element of quality control that goes on. If it's late, if the pizza's not up to standard. So even the sort of managerial approach of, I'm going to pay somebody else to do this for me, needs an amount of, who do you choose to do this? How do you ensure that they've done the job properly? So don't assume that somebody is doing it right at that top level hasn't also had to think through some really quite difficult questions there. So yeah, all of this, so much of this computational thinking you can do through the medium of making pizza, but if you do the making pizza exercise with your class and get them to write down their recipe for pizza, please don't stop at this point. Let them make the pizza. Yeah? There is nothing worse than the D&T lesson where they write down the recipe of pizza or make the box for the pizza and don't have the experience of baking, of making the pizza. And the same, I think, applies to much of the computational thinking. I love a lot of these unplugged approaches, things like the phonics, things like the pizza, but actually writing the code, baking the pizza or making the pizza is the equivalent of that. So that takes me on eventually to...
Miles, I'm so sorry. I forgot 10 grams of salt. It wouldn't have tasted the same.
No. Sorry, we will get back to computing in a moment.
Just in case anybody was taking down the
I'm
recipe.
sure they will. We've got a recording of this one. But I've done this with Roehampton trainees. The postgrads are usually pretty good at this, but I've got undergrads who put in eggs to their pizza dough. I think they're making cake at this point. But again, debug the instructions. That becomes very apparent when you actually have a go at making the pizza. You might not want to do that with the class. So what about the coding? Well, we use the words programming and coding semi-interchangeably, but I think it is worth having a distinction between the two. Programming a computer, getting a computer to solve a problem for you, to simulate a system, to do something, is always a two-step process. The first step is thinking about the problem, understanding the system, coming up with the scary 5-syllable word algorithm there, the sequence of steps, the sets of rules that you need to make that happen. Then and only then do you actually start dragging blocks around or putting fingers on keyboards and writing the code that implements the algorithm. Same algorithm, lots and lots of different implementations of that. And that's fine. You can learn to do it in Scratch or Scratch Junior or other products, and then in secondary school they'll learn about Python or other text-based languages. That's fine. But still a two-step process. And the algorithmic thinking is really, really important. But the coding is really important too. So try and keep the two together there. Can you do one without the other? Yes. You can do recipes for pizza. Or you can follow instructions down the left-hand side of the screen and write some code on the right-hand side of the screen. But it's really when the two come together that the most interesting stuff happens in programming terms, I would suggest. So we want, yes, the computational thinking, but we also want the computational doing. Jeanette Wing, who coined the term computational thinking, talks about it as the thought processes involved in formulating problems and solutions so that the solutions can be represented in a form that can be carried out effectively by an information processing agent. In other words, can be expressed as code, that we can make a machine or a computer do these things as well as thinking about them. And again, Kaz Barefoot, we've got that. We've got the think about the problem. We've got the sort of lovely play with Scratch Junior, make the fish tank scene. We've got write out your algorithm for the Bee-bot. We've got plan the Viking invasion as a Scratch animation. We've got can you identify what the stages are for the water cycle there. So we're taking ideas from across the curriculum and linking them to really useful, interesting, practical programming tasks. I want to this afternoon, though, in the little bit of time we have left, go a little bit further than that. Using other bits of the curriculum to motivate the programming is fine, but I want to go a bit further. Stuart talked to us earlier about Seymour Pappert's work. Here's the book Mindstorms. In there, Papert talks about what he saw happening when he went into school and taught children to move floor turtles around the carpet. He began to see how children who'd learnt to program computers could use very concrete computer models to think about thinking, to learn about learning, what EEF call metacognition these days. In doing so, enhance their powers as psychologists and epistemologists. For Papert, the programming was not an end in itself. It was through programming that the children started looking at problems differently, started understanding ideas from maths, from science, from what Papert called the art of intellectual model building, because of this experience of writing programs for computers to do things. So, 2 years into the national curriculum, your mileage may vary here. I think in some schools, we're kind of getting to the point where some pupils are actually getting quite good at coding. True? Really? It's so nice to hear that. Does anybody want to contradict me? Say this hasn't actually worked. This is interesting data. Okay, tweet me or come and talk to me afterwards. But I think 2 years in, we've overcome our initial fear of this. We've got some interesting activities. We've got to the point where, yeah, a child can write a Scratch program, and it does something. They can start expressing themselves through this medium of code. And once we've got to that point, then so many more possibilities start to open up. We can start, just as we used to use PowerPoint as a way to teach children about history, or we used to use Word as a way to teach children things in English. We're now kind of getting close to the point where we can use Scratch and other programming languages to teach children things about other parts of the curriculum. And that's slightly different from just taking a context and using some programming here. So the big idea, you want to take the photo at this point, this is the nub of the talk, that I think we're at the point where you can look for ways that your pupils can apply their coding skills and the rest of their computer science knowledge to solve problems and develop understanding in the other subjects that they have to study at primary school. I may be quite naive here, but I think in some schools we're kind of there. So yeah, what I'm going to do now is quite quickly go through 10 other subjects and see how we could use some of the computer science bits to teach bits of that subject. So let's start, of course, with English. So much of the text that your pupils read isn't in books, despite the reference to books in the national curriculum. Your pupils are routinely reading text which is prepared only for the web. Isn't there a place, if that's the medium that they're reading it in, to teach them something about how to write text online? How to actually get to the nub of what we call HTML, hypertext markup the language in which the web is written, and to start making their own web pages. Yes, you can use the lovely drag and drop interfaces. You can do all of this in Google Docs. You have to forgive me sitting down at this point because I can't code while standing up. So we've got tools like Thimble here from our friends at Mozilla, the people who bring you Firefox. And here's one I prepared earlier, but we can take all of this text about Tim Berners-Lee and just get rid of that and start typing some new text in here. So I want to make this a heading. I do H1 for a big heading. This is my big heading. Okay, and then we can start a new paragraph. The HTML code for paragraph is P, and then this is my introductory paragraph. And I can start typing that. And okay, it feels a lot like word processing, but I think there's a couple of advantages of doing this over word processing. Firstly, you focus on the structure of the document that you're writing here, not which font am I going to use? Which color am I going to put this in? You just get down there and start writing some text. The other thing, which this does that Word and other word processors doesn't, is we start getting used to this idea of code, that in order to get this to do something, I need to write the instructions on the left-hand side of the screen. And I see the result immediately on the right-hand side of the screen. I said earlier, don't separate out algorithm and code. But here we do in HTML because we only focus on the code. There is no algorithm that I'm implementing here. We can take a picture off of the internet. Sorry, I should have done this earlier. Let's go off and find a picture of Tim Berners-Lee, inventor of the web. Sorry, Tim Berners-Lee. Some images. Okay. You notice I have Safe Search on. Please make sure you always have Safe Search on when doing a Google image search. It's not perfect, but it's not bad. So we've got the code here, the address on the internet of where that picture is. I can come back over to my Mozilla editor and type in the code to insert that picture. So I do image, I do source equals, and then paste in that HTML, and then end the image tag, and there the picture appears. If I want to change the width of that, I've got a command I can give it here. Width equals 200 pixels, and that shrinks it down in proportion. Now, I'm not going to teach you HTML this afternoon, but getting children to play with this, I think, is a really nice way into understanding how web pages are written. So that's over in English. Let's have a look at some maths now. So what about this one? Here's some Scratch code. Let me walk you through this. So we've got this idea of pi, the area of a circle, or the ratio of the distance around the edge of a circle to the distance across the circle. But this isn't doing circles that way. This isn't a program which appears to be drawing a circle. Let's just have a look at the code here. We wait a little while, we initialize two variables, and then we repeat something 1,000,000 times. What do? We pick a random position in 180 by 180 square. We go to that position. If it's less than 180 dots from the middle of the screen, we color it in green. Otherwise, we color it in blue. And we keep on doing that. We make a little dot 1,000,000 times. If it's within 180 from the center of the screen, color it in green. If it's bigger than 180 from the center of the screen, color it in blue. Can you predict what this is going to look like? Very good, thank you. Okay, so let's set the thing running and see how it goes. So there we go, that's 50 dots already. Can you start to see them appearing up at the top left? This could take us a little while. But we've got turbo mode here, so let's speed it up. And that's 100,000 dots all plotted, 250,000 dots, and eventually we get to the 1,000,000 mark. And you've got 1,000,000 dots drawn according to that rule. Anything less than 180 is colored green, anything bigger than 180 is colored blue. And of course, if you divide one by t'other, the area of the circle, you've got the area of the circle compared to the area of the square, and you have there a very good estimate for pi, 3.140668. How could we make this more accurate? Do this more than 1,000,000 times. Doing this without a computer would keep them busy all term, okay? Doing it with a computer I can do when I'm worried about getting to an airport for later today. Okay, so what else have we got? We've got the science stuff. So the classification key thing. Let's put the picture back up on the screen here. So, not that one. Not that one. Classification keys, which we teach relatively early on. So, how can you tell what a thing is? This is what actual botanists, zoologists do at places like the Natural History Museum. They have the definitive classification key, and they ask yes/no questions. This structure here, this tree, is fundamental to so much computer science. And we used to have the whole branching database thing, but you can write a program to do this in Scratch. I've actually gone into Python here, which is text-based programming language, which, we kind of would introduce at key stage 3, and we can run the code. So step out of the deck, move into the thing here. Let's make that a little bigger so you can see it. So I'm defining some procedures. We start with this one. Does it have legs? If they answer yes, we go to the legs procedure. If they answer no, we go to the no legs procedure. If they try to be amusing, we give them some feedback. That's not one of the choices. Do as you're told, please, children. Important that they learn that lesson. And then we go through the legs procedure. Then ask, does it have 6 legs? Now, writing this, okay, you've got to master the Python syntax. You can do it in Scratch. But once you've got that idea, then what you're looking at is actually the yes/no questions which we have in science. So I'm going to run this code with a little bit of luck here. And then we answer the questions. Does anybody want to pick a mini beast of their choice? Anybody have a favorite mini beast? Ladybird. Thank you. Let's see how far it goes. Who's the ladybird person? Okay, does it have legs?
Yes.
Very good. Does it have 6 legs?
Yes.
You have an insect. Okay, and then we'd need to, sorry, I've not done all billion different types of insects in here yet, but, there's an exercise for your class. We can add some more questions in and start distinguishing between one insect and another, yeah? So we can add more layers to that. This code is exactly the same code as you would use if making a text-based adventure. Anybody old enough to remember Fighting Fantasy adventure books Okay, right, you surprised me, both of you. But, you know, do you want to attack the dragon or run away from the dragon, turn to page 38, turn to page 96. You can do exactly the same thing using this branching database. What option, you know, go this way for one, go that way for the other. We've got Year 6 children doing that in Switched On Computing Commercial Scheme of Work I've been involved with already this year. So they're writing Python code to do the text-based adventure games. But I think it gets really interesting when you link it to these ideas in science and how we classify different things. What else to show you? So into art and design territory, let's make the blocks a little bigger here. So this one is a bit strange here. Clue in the title of the block here, but I'm going to draw some trees, it would appear. And my definition, have you looked at broccoli? Have you looked at trees? What do trees, what do broccoli have in common? Yeah, okay, one bit of broccoli looks like a lot of broccoli. One bit of a tree looks like a lot of a tree. We have this fractal nature of the world, that a little bit of it looks like a lot of it. And that's essentially what my code here does. So my tree is defined such that if the size is big enough, then I move up, I turn to the left, and draw another tree. Then I move back, turn to the right, draw another tree. I keep doing that until my trees get small enough that I think that's quite enough trees. Thank you very much. So let's run the code and see what the turtle does here. Okay, and it's going to take a little while over doing that. Again, turbo mode is our friend. Okay. Now, of course, and tweaking these numbers will get you a different picture out of it. So we've got something there about the aesthetics of nature, but that's, you know, is that a beautiful thing? Getting a chance to draw a tree with that level of detail, really hard. Getting a chance to draw a tree with that level of detail on a computer. Okay, I'm not saying this is easy, but you can scaffold this and you can help them learn this. And then you get into this interesting conversation around, well, how come so much of nature has this sort of, the closer you look at it, the more detail you see nature. And I think that's part of art and design education. The art specialists in the room may wish to contradict me at this point. I got away with it? Okay. Right, that's good. Okay, what else can I show you? Oh yes, and then we get into foreign languages? No, let me just go back to the slide deck here. So that was the sciencey bit. Then we talked about art. I'm not going to show you the DT video because you've already had a go with the Lego We Do kit. But over in the design and technology curriculum, it talks about children making products and then using their computing to control and monitor what those products do. And you can do that with Lego We Do very, very nicely. So we'll skip that bit and then get into foreign language territory here. So here we go. Again, let's make this larger for you. So we have here modeling the foreign language conversation in Scratch, which is fine. But what we can do is swap the language pack over. So rather than programming Scratch in English, I can move en français and then have my programming blocks there in the target language. And this works really very well if you have EAL pupils in your class. If you've got children who don't speak any English but still want to come to your computing lessons, and why wouldn't they, swap Scratch into their home language and let them program Scratch in their mother tongue. So we click on the green flag, and it doesn't work properly. They both say things at exactly the same time. So we've got to build in some sort of wait instructions here. So attendre une seconde. I think we're going to need 2 secondes in there, and 2 seconds in there, and 2 seconds in there. And then the other one, I think we want it to wait before the conversation starts. 2 seconds. And 2 seconds at that point, and 2 seconds at that point. Let's run the code and see what happens. Okay, bonjour. Bonjour. Ça va? Ça va, merci, ça va. And so on. Okay, you have to bear in mind I gave up French at the age of 13, so don't expect too much of me here. You've also, of course, in Scratch, got the ability to record a sound. So on the son menu here, we can listen to meow. Sounds very, very similar to an English cat doing meow as well. Or we can record our own. Let's have a go at this. Yeah, that's absolutely fine. Bonjour. Oh, absolutely fine. Bonjour. Oh, And I think we need to edit a little bit of that out of there. Editing skills really important. Okay. Bonjour. That's horrible, isn't it? Right. So we can have that on the son menu. Je le sens. I call this meow still, which is really embarrassing. Bonjour. And you could do the rest of that, but I'm not going to demo that now. Okay, so that was foreign languages. I want to show you some of the cool stuff you can do in terms of geography. Now, the geography stuff is the example, the language I'm using here is Python, but you can do a lot of the analysis using something as simple as Excel. Anybody got Raspberry Pis in their school? What are you doing with them?
Nothing yet, it's just arrived.
Oh, that's going to be so exciting. Okay, you've got Raspberry Pis?
Yeah, they're not doing anything.
Oh, in a cupboard somewhere. You never know when they may come in handy. Okay, one of the lovely things you can do with a Raspberry Pi is set up a school weather station. And there's so much interesting data analysis, getting children up and presenting as if it were a weather forecast. That's nice too. And getting children to be able to, use that data to make predictions. It's hard. We know that forecasting the weather is hard, but it's an interesting thing to do in our country. I've done similar things in other countries. So, like for Egyptian schools, we had this unit about, can you predict what the weather is? And I say, well, yes, it's going to be really sunny. So it becomes a slightly easier task in other locations, apparently. Anyhow, so if you've not got the weather station yet, you can get the weather data. And Oxford significantly has really good weather data going back as far as, I think, 1854. So you download that from the Met Office website. It gives you a month-by-month summary of the weather in Oxford going back to 1854. So here it is bringing the data in from actually 1853 all the way up to September. We have month-on-month records of what the weather has been like. So we can have a look at the average monthly maximum, the average monthly minimum, and we find out that's 13.9 and 6.2. Fascinating, isn't it? We can look at the spread of that data, and you've got that. We can do a histogram of that. And that's hard to do a histogram in Excel, believe it or not. So there we go. That's the spread of the monthly minimum temperatures in Oxford back as far as 1853. Some months are hotter, some months are colder. That shouldn't come as a surprise. What you find is that generally, the more sunshine there is in a month, the warmer the month is. There's an expression of surprise from around the room, but there's the data, there's the scatter plot. There are exceptions, and of course we could drill down into the details. So this was quite a sunny month, but a really cold month. We're thinking, one of those lovely, bright, brittle Januaries. So you've got that there if you want it. We can code it up with the date of that, so we can ask interesting questions like, what was the weather like 10 years ago? Anybody remember? Well, it was like that. A pretty ordinary October, I'd have thought, just looking at the figures there. We can look at when the cold months were. What do I mean by a cold month? One where the average minimum temperature is below zero, or the number of days when it's been freezing is more than half of the month. So that's a really cold month. Let's have a look at those cold months. Loads of them back in the 1850s, 1860s, 1870s, some really, really cold months back in the middle of the 19th century. Who knew? But more recently, well, not many more recently. Only 3 cold months since 2010. Only 2 cold months in the whole of the 2000s. Not many in the 1990s either. That's interesting. That seems to have changed. We can have a look at how that's changed over time. We can plot the maximum and minimum temperatures, and here's the graph. And getting children to plot that is going to take them a while. What do you see with this graph? Well, it's really spiky. Yeah, that's generally because summer months are warmer than winter months, so you've got a big sort of month-on-month variation in maximum and minimum temperatures. But we can smooth that out. So this last 2 lines of code here smooths that out, and you look at the trend in maximum temperature over a 5-yearly moving average. And here's your graph. So recently, that 5-yearly monthly maximum temperature seems significantly higher than it was 100 years ago. In fact, significantly higher than it was 30 or 40 years ago. Evidence of global warming? Well, One assumes that the Oxford people who supply data to the Met Office were reasonably good at that, even in the 1890s. I don't think accuracy would explain the difference there, but yeah, there seems some difference. So you can get into those sorts of interesting questions through writing code to do that. And okay, this code is relatively sophisticated, I'll acknowledge, but I think the project is an interesting one, and doing it in Excel is a legitimate thing to do. What about history? Oh, there's this lovely thing in the history curriculum about taking a topic not on the list and looking at how that has changed since 1066. And one topic you could do is the sort of history of communication, or the history of communicating in code, cryptography. So I can zoom these blocks so they're a little bit larger for you to see here. Okay, that's fine, maybe. Is it going to show me these again? Okay, and what I've got here is writing in Snap, which is a language like Scratch. I've got something which will play me Morse code for a particular thing. Maybe. Okay, or not. I've got something here which will do me an encryption of a message. So Caesar cipher is shifting everything along one space in the alphabet. So I can take a message here and encode it from one alphabet to another. Oh, and that's just not working. So let's try that once more. Okay, so there you just about can see. I think I need to change the zoom setting back. That was me trying to be helpful, which wasn't. There you go. So let's try that once more. So there you go. So taking the letters of the word hello and shifting them all one place along the alphabet, you get LFMMP or something along those lines. So you've got that idea of creating a code, and then of course children can then come along and crack the code, and we can come up with much more sophisticated codes than just moving things around the alphabet one point. And of course there's lots of this links to really interesting topics in history, and I hope people are thinking of Bletchley Park, Alan Turing, and cracking the Enigma code, but there's lots more to it than that. This notion of shifting things along the alphabet, one or in some cases three places, called the Caesar cipher, named after Julius Caesar. Back 2,000 years ago, this was state-of-the-art cryptography. Watch what you're doing with cryptography, because there are people who get arrested for terrorism offences for teaching cryptography, it seems. Okay, what else have we got there? Oh, what about music? What about PE? You can do lots and lots of music in Scratch, really nice music toolkit. There's a lovely thing called Sonic Pi, which isn't just for the Raspberry Pi, which plays music beautifully. I'm worried about the audio not working, but let's see how we get on here. You get the idea, and no comment on Brexit is implied by this. But we have there a procedure. This sequence 1 is the repeating block of notes. And then we call sequence 1 and then play some more notes. Sequence 1, play some more notes. So we have there a representation of the audio that you've just heard through the medium of code. And getting children to play with that way of representing music, I think, is an interesting thing and extends their understanding of music. And for some children who really struggle to play an instrument or to sing, why not give them another medium that they can work in there? I hope you can all imagine somebody in your class to whom that sort of thing might appeal. What about PE? Well, the Fitbit is the obvious one, but this is fun too. So this is a thing called Connect to Scratch, Xbox Connect sensor. Plug it into Scratch, get children dancing in front of the Xbox, controlling things in their Scratch program. Maybe. Okay.
So here we have a skeleton representation of the Connect data.
You see it moving at the bottom there?
Recorded in Scratch, as you can see, in full screen mode and our presentation mode. And the Scratch cat here has gotten a new body, and the joints are being controlled by me, as you can see. There's only certain joints available, and there may be more in the future, such as fingertip joints and so on, but currently...
I could imagine that being such fun. I really could. You know, if you've got the kit, use the kit for that sort of thing. The Fitbit stuff is worth doing as well. Again, takes you down the data analysis thing. Anybody you got microbits, the BBC microbits? They're intended for secondary schools, but you're allowed to get them now. And you can use a microbit as a fitness tracker and get children building their own Fitbit or Fitbit equivalents. I move into PSHE here, and I have a little racing car game. What on earth is he doing using a racing car game to illustrate PSHE? Well, let's have a look at the racing car game. So this is actually an autonomous racing car. It says, if the yellow thing touches the grass, then turn right. If the blue thing touches the grass, turn left, and keep going round the track. So let's run the code, and it chugs away pretty much autonomously like that. That's fine. But what happens if we increase the speed? If I turn the speed up to 20 here rather than 3, oh no, we lose control. Is that a bug in the code, or is that really just a very good simulation? If you drive too quickly, you will lose control of the car. Well, relatively trivial point in PSHE, but this is kind of what's going on when it comes to our friends at Google and Uber and Mercedes and Audi producing cars that will drive themselves. I assume the code for Google self-driving cars is a little bit more sophisticated than this. If they're just using Scratch for it, worry, be afraid, be very afraid. But somewhere in there, there will be the instruction which says, if you hit the left-hand side of the road, turn to the right. If you hit the centre of the road, turn to the left. You've got to have that sort of instruction sooner or later. If the child runs out in front of you, apply the brakes. In fact, if anybody runs out in front of you, apply the brakes. And so we get into the interesting PSHE conversation about what are the, not what are the rules of driving, but what are the ethical rules about Google self-driving cars? If the Google or indeed other self-driving car manufacturers, the self-driving car has the choice of killing 1 pedestrian or killing 20 pedestrians, and that is the only alternative, what should it do? Well, 1 is the kind of the obvious answer here, isn't it? Yeah? You hope that it never comes down to that choice. Well, yeah. There's an ISO out now about what the ethical principles for robots will have to be. And it's not Asimov's rules, interestingly. But, you know, that situation is a relatively easy one. What about if your choice is knocking down the pedestrian or preserving the life of the driver? What should the self-driving car do at that point? What would you as a driver do at that point? You get into some really interesting ethical territory. And the German government are already playing with this, as is indeed the International Standards Organization. German government are looking at these 3 rules. Property damage always takes precedence over personal injury. If the choice is between hurting a person or hurting property, then hurt the property. And there shouldn't be any sort of bias built into this. It shouldn't matter if somebody happens to be a Mercedes owner or a Google customer. The properties of the person shouldn't determine the action of the car. And that the manufacturer is liable. It's not the person who's sat in the car. If you're drunk and get a taxi home and the taxi crashes into somebody, it's not your fault. Yeah? That it's the same if in the self-driving car. So you get into some really interesting ethical conversations. And we have there on the lovely CAS community site loads of resources about teaching children about binary, which is really important. But we don't have nearly enough about getting children to think through the ethics of when machines become autonomous. And that's going to be really soon, folks. It really is. The decisions made about your credit card are not made by people anymore. It's machines that are making those decisions. And finally, RE, and there's just so many lovely things around RE in computing, of which my favourite is the example of Islamic art, because Islamic art has this tradition of not representing flowers or animals or people, or of course the Prophet. But Islamic art takes as its tradition sort of this notion of geometry as a beautiful thing, and so getting children to play with geometry, and yes, make the repeating pattern, and then think about yes, the aesthetic properties, but also think about why Islamic art has this strong emphasis on not representing living things as part of its tradition, I think is something which we can get to through computing. I'm about to wrap up. You'll be delighted to hear. The question, if we had time to discuss to you, would be, which of these would work with your pupils, with your colleagues, with your schools? Is this too ambitious yet? 3 years' time, maybe, but not quite yet, Miles. Or, yeah, there are things that that I can take home and do. I'm not trying to sell you this, but I want to mention switched on computing, commercial scheme of work, and then reusing it. Okay, you're not using it though. Okay. That's fine. Yeah, it says you're allowed to do that, and you are allowed to do that. But what we try to do with switched on computing is take real-world authentic contexts for using computers and really emphasize the cross-curricular links there. So you can do it, even if you don't want to buy the scheme. You can download the big master plan and have a look at that and use that perhaps as a point of inspiration. If you're interested in building up your own computer science subject knowledge and a knowledge of how to teach it, then can we mention the CAS certificate, no, the BCS certificate in computer science teaching, Nadine?
So the BCS certificate in computer science teaching helps you develop your programming and teaching skills and accredits you with those skills. We actually have an online Scratch course starting in November, which guides you through Scratch. So if you're not familiar with Scratch, you'd like to learn it, it's 8 weeks and it only costs 60 quid. You have a tutor who helps you through it all, and it's very popular. But we've got some spaces, so do have a look on the CAS website for that.
Thank you. And finally, if all of that is, yeah, I've been doing that in school for like 2 years now, Mark, do have a look at this thing about the CAS Master Teachers. Computing School has this network of excellence. We've got nearly 400 teachers who are sharing their knowledge of computer science, their brilliant classroom practice with the teachers around them, 40 or so schools near them. They take on that role of being the person to talk to about how to do this. This is funded by the Department for Education, seen as a very good thing. You'll notice on the map, though, like the Oxford donut here, there is one CAS Master teacher, I think secondary, in Oxford. If you sat there and think, yeah, I know enough about this, I could do this, I'd like to share my knowledge with others, then please do get in touch with Tig Williams at Southampton University and say, yeah, I listened to Master's talk and I think I could do that. I could be a CAS Master teacher. You have to forgive the gender-specific language. It was a DFE thing, Master teacher. You know, it's open to women as well as men. Really is. Okay, so that's the CAS Master teacher thing. Thank you ever so much. I don't want to take questions from the floor in case you ask me things I can't answer. No, because we all probably want to do the evaluation forms and get home. So I'll hang around for a little bit, or tweet me, or get in touch via email. But thank you so much for listening and joining in for this very late session today. Thank you.
Thank you very much, Miles.